Hello everyone, my name is Infantri Siahaan and I'm from Mechanical Engineering of Udayana University. And now I want to explain about my presentation about discovering metals, a historical overview. And the reference I take from this book with title Metallurgy for the Non-Metallurgists, second edition, edited by Arthur C. Riordan. And the topic that I will explain is native metals, the Bronze Age, making metals, extractive practice, iron, discovery of modern metals, and refining of metals. Let's begin. The progression of human civilization from the Stone Age to our modern society has been marked by a growing dependence on metals and alloys. Over millennia, our understanding of metallurgy has advanced significantly, evolving from a rudimentary craft to a complex science. Beginning with the discovery of copper, early humans were driven by curiosity to explore the properties of metals. This exploration led to the accumulation of substantial knowledge about how different metals and alloys behave. The journey of metallurgy, documented up to the electrolytic refining of aluminum in 1884, illustrates this fascinating historical evolution. And this is the table of chronological list of development in the use of material. You can see how first human met to do some materials. You can see here from 9000 before century until nowadays in 1884. The first earliest metal objects of rock native copper until we see human can do electrolytic refining of aluminum. Native metals. The majority of metals are typically found in nature as part of minerals or compounds, resulting from reaction between metal atoms and other metals or non-metals. A key objective for metallurgists is to extract metals from these compounds. Native metals, which are relatively rare and occur in a combined state, are important in the field of metallurgy. The utilization of native metal played a foundational role in the emergence and advancement of metallurgical science. In ancient times, humans initially employed naturally found, relatively pure metals like gold, silver, and copper. Gold nuggets, often discovered alongside quartz sands in rival beds worldwide, were shaped into decorative items, but due to their low strength, they were unsuitable for practical tools or weapons. However, gold's shiny and lustrous properties made it highly valuable for jewelry and as a symbol of wealth. Next is silver, though less abundant, was also utilized similarly. Even naturally occurring mixture of silver and gold, known as alloys, had little practical utility. Historians often regard the Copper Age as precursor to the Bronze Age, as the utilization of copper, particularly copper alloys, marked the beginning of practical metallurgy. The next is the Bronze Age. The Bronze Age is a historic period lasting approximately from 3000 before century to 1500 before century, in which metal was used for the first time. The term also refers to the development of material culture and urban civilization among the ancient peoples of Europe, Asia, and the Middle East. The Bronze Age is characterized by the use of bronze, a metal alloy of copper and tin, and the presence of writing in some areas. Bronze was significantly stronger than relatively pure copper and was useful both as a tool and as a weapon. A photograph of an ancient bronze casting is shown in figure 4.1. This casting is an example of the high level of perfection achieved in Chinese foundry. technology in the 7th century before century. The bronze in this casting contained less tin than was typical of bronze weapons from the same area. So here is the bronze quay from China. This is the people there call this technology because this bronze contain less tin than the usually bronze. So the next topic is extractive practice. Schematic of a lead blast furnace for smelting the galena ores is illustrated in this picture in figure 4.2. Basically, such processes are the key to any pyrometallurgical extraction process. An ore is heated in the presence of a selected and controlled environment. This environment reacts with the ore to produce both the desired metal and the other products of the smelting reaction. To illustrate the undesirable nature of some smelting reaction products, note that the hydrogen sulfide gas produced by lead smelting is poisonous. Lead smelting was successful because at temperatures commonly reached in a wood fire. Oxygen in the air reacted with the lead sulfide to free the lead and produce both sulfur dioxide and hydrogen sulfide gas. Next topic is iron. Unlike the reduction of copper sulfide ores, field smelting of iron is not practical because higher temperatures and a more carefully controlled environment are needed. Smelting of iron oxides requires some carbon or carbon monoxide to react with the iron oxide to produce iron and carbon dioxide. Early iron smelting operations were conducted in chimney furnaces, such as this picture. This furnace could easily have been developed after the first accidental reduction of iron oxide. The temperature in a blast furnace are approximately 1500 to 2000 degrees Celsius because of a rising stream of hot carbon monoxide that results from combustion or burning of the coke. At this temperature, the carbon monoxide began to react with the iron ore to free some of the iron. At the same time, some of the carbon monoxide is cooled by the charge and forms carbon dioxide and free carbon. Okay, now we go to this topic, discovery of modern metals. The convention of using the Latin suffix in naming metals, as seen in examples like beryllium, become common for metal discovered or isolated after 1800. These metals often hold significant commercial value, largely due to their role as alloying agents. Alloying elements are typically incorporated to enhance the mechanical, electrical, or chemical characteristics of other metals, similar to the way tin strengthens copper. Subsequent sections will outline various commercial applications for several of these metals. So, for the modern metals such as beryllium, cadmium, chromium, molybdenum, tungsten, vanadium, magnesium, here titanium, iridium, rhodium, palladium, platinum, and aluminum. So, the last topic is refining of metals. Refining of metals refers to process that purify extracted metal. Refining of metals, like the extraction of metal from ores, includes many ancient practices and more modern advances. Refining techniques for most metals are much more complicated but involve similar phenomena. Many techniques now used were not developed until quite recent times. Today, refining can be used to produce very pure metals. Copper, gold, silver, aluminum, iron, and many other metals can be purchased at purity levels of 99+%, which is equivalent to 1 part impurity in a million. Okay, that I can explain about my presentation. Thank you for your attention, everyone. And if I have wrong way to explain my presentation, I'm really sorry. Thank you.